So today we're going to talk about lazy execution, something that all programmers love very much. We do as little work as possible, but here it's the program that's doing a little bit of work. So I'm going to talk about lazy evaluation. Lazy evaluation is just a form of functional programming. So I'm going to give many examples. Lazy, I'll show you how it works by defining some lazy functions. I will give you the semantics, so you see exactly how the magic is working. And then we'll talk about how to use it. Lazy streams. I'll talk about infinite lists. I'll talk about some interesting problems. One is called the Hamming problem, which shows you the kind of programming techniques you can use when you have lazy evaluation. And then we'll go into how it executes. So I'll talk about lazy suspensions. So in this course, it's not enough for you to program with lazy. You have to understand how it works also. And then I'll give a more complicated, a more sophisticated example called the bounded buffer. And I will end with lazy quicksort. Here is where the laziness will actually invent an algorithm. So the lazy computation will do as little work as possible. So this is a property of how it evaluates. And in fact, in the previous course, we saw in the lambda calculus, we saw that there's applicative order and normal order. I didn't say so much about it, but applicative order is the normal way of executing when you execute the arguments before calling the function. But in normal order, you will not do that. You do just the opposite. You will execute as much as possible of the function and only execute the arguments if you really need them. Okay? So that corresponds to lazy evaluation. Okay, so this time I'm going to give you a lot of code examples. So let me first, so the examples I'm going to give you, the code I'm going to write here, I'm going to put it on the Moodle after. So let me first start by doing a simple introduction to continue what we did last week. Deterministic data flow with streams. This will put you in the mindset of this kind of concurrent programming. So I will have two agents. One of them is a producer, and the other one is a consumer, making a stream. Okay. And both of these will be executing concurrently. So let me define a producer. So this will define a list of numbers going from L to H. It's very simple actually. If L is greater than H, then nil. Otherwise, L followed by prod L plus 1 H. Okay. So that's a producer. And then I will actually, in order to make this clear what it's doing, let me put a delay here. So the delay will tell the scheduler to wait for 1000 milliseconds. So the thread will go slower, so we can see how it's executing. And now let me make a consumer. So this consumer will take a stream as input, and let's say it has an accumulating argument. So it will compute the accumulative sum of this list. So 1, 2, 3, for example, if one of them produces 1, 2, 3, then it will be 1, 3, 6, and so on. It'll do the cumulative sum. Okay, so I will read the list, H, T, and the result will be accumulator plus H, followed by recursive call. Okay? And when it's done, it's done. Okay, so this is a consumer. So you see these are two very simple list functions. Huh? Producer just makes a list, and consumer just computes one list with another. And in fact, you can call them as normal list functions. So let me compile these. This way. So for example, I can do browse prod 110. Okay, it's actually running now. It's not giving anything. You know why? It's because of the delays. But after 10 seconds, then the function completes. So you see, basically, you have to wait for 10 seconds before it shows you the result. But then it shows everything. Okay. Let's now run this concurrently. Okay, so now I have the same program as before, this producer, and I'm going to display the results as the producer runs. So remember, before we had to wait 10 seconds, and then we saw everything, okay? But when we run this concurrently, it's going to run differently. So you can see every second a number appears, and both of them are appearing concurrently, okay? Now you can see the results here are the same, from 1 to 10, from 1 to 10. And then there's also the second result. It's displayed a little bit differently, but these two lists are identical. Huh? It's using the bracket notation. The browse uses the bracket when it knows that it's a list. Whereas when I create it incrementally, the end is still unbound variable, so it doesn't know. So that's why it uses the vertical bar notation. But in fact, both of those are exactly the same. Okay? So this is an example of the deterministic data flow, concurrency. So this is a pipeline between producer and consumer. Okay? So this, I show you this. This is actually continuing what we started last week, to refresh your memory on the deterministic data flow. Now, in the previous course, we saw many bigger programs. Okay? Remember, we saw even a digital logic simulation where you can do adders and latches and huge things with a huge number of threads, and it's all deterministic data flow. So I'm not going to repeat that today. I just wanted to show you how that this deterministic data flow between this producer-consumer makes everything go incremental. Okay? Okay, so that's continuing from last week. Now let me talk about lazy computation. So here's a simple example. Let me define a lazy function. And in Rust, you can do that by using the keyword lazy when you define the function. Let me call this one lazy add x plus y. It's very simple. It's just doing addition, right? So this function, lazy add, is just doing x plus y. And now let me do the sum. Let me call lazy add of 10 and 20. Browse S. Okay, let me make this one smaller like this. So here I'm calling the function, and then I will display the result in lazy computation. So you can see that nothing is displayed here. An unbound variable. So what's happening here? When I call this function, it does not actually execute the function. Okay? A lazy function, it actually creates a lazy suspension, which I'll explain in a minute, and it does not actually evaluate this function. So how do we evaluate the function then? Here the browse will display something without evaluating it. It will just display, so it displays unbound variable here. So this lazy suspension is waiting until the result of the function is needed. Okay? So the lazy evaluation will only evaluate things when they're needed. So here, so what does that mean, needed? Okay, well, I'll explain it to you. S is needed when I do another operation that can only complete with the value of S. So for example, if I do browse S plus 100, I do an addition. The addition will need S. In order to complete, the addition needs the value of S, and this will trigger the evaluation. So you can see the evaluation is triggered in the opposite direction from regular computation. Regular computation, I call a function and I evaluate, and then I call another function and I evaluate, and so on. And lazy evaluation does not work like that. So let me execute this. So when I execute this, you can see I now display 30 and 130. So now I evaluate this. So this lazy addition is only evaluated when I need the value of S. Okay? So that's actually a very simple idea. Let me explain the semantics of this. So how does this work? How does this lazy function work? Let me see if I can write it down. Let me explain how it works, and then we'll show some programming techniques. So this is a very simple example, huh? But you can do extremely sophisticated programming using this idea, and that's what I'm going to show you today. So, if I have a function, let's see if I have a piece of chalk that gives me a darker. Oh, this is very cheap chalk. Maybe this one is better. You can almost not see it. I think I will have to buy my own chalk. Maybe this one is better. You'll be able to see it. It's a little bit better. Fun, lazy add, x, y. It does x plus y. But how is this actually executed? Well, it executes, it has a new operation. There's a new operation in the language called wait needed. So in fact, I'm going to translate this to kernel language so that you can understand how it executes. So remember in the previous course, we saw the semantics of all the operations, and you can do that by translating them into kernel language and then giving the semantics of the kernel language operations. So this is translated as follows. It's translated into a procedure called lazy add, x, y, with one extra argument, which is the result. Okay. It creates a thread, and inside this thread, it does an operation called wait needed, r, and then it does r equal x plus y. So the body of the function here, you can see it again here, huh? But you can see we're doing something around it here. We create a thread, and this thread does an operation called wait needed. on the result. So it waits until the result is needed by somebody. So I'll show you in a minute how that works. And when the result is needed, then it computes it, x plus y. So r equal x plus y. That means when you call the function, it creates this thread that waits. Okay? So this thing, I call it a lazy suspension. Okay? So a lazy suspension is actually a thread that will wait until the result is needed. Okay? Let me show you how the wait needed works now. Okay? So let's explain the wait needed operation. So let me declare a variable x, and I do wait needed x, and then I do x equal 100. Okay? So this will block. So I execute this, and now when I display x, it's displaying an unbound variable. You see? So what happens is this operation will block the thread. It will wait. It will wait until x is needed. So that's something that we have to define, okay? So it blocks here. So what does it mean that x is needed? So it will wait until x is needed. I put it in quotes because we have to define this. So needed means that another operation needs the value to complete. So for example, if I do x plus 10, this operation needs x. Okay? Or if I do a case statement, if x is a list, in this case it's not a list. Again, the case statement needs the value of x, okay? Or if x is a record, if I do x dot and then some field, name, which is because it's a record, again, the dot operation needs x, okay? So the wait needed will block until I do something that needs x, something like this. Okay? So browse x does not need x. So you see the browse is a very special operation. When I display with browse x, it doesn't actually need the value of x to display it. Okay? So this will block forever until somebody needs x. Okay, so, yeah?
What is the cost of waiting forever, as you said?
The cost of waiting forever. Okay, so what happens is that when I execute this is operating in a thread. This thread will block here until x is needed. So if x is never needed, then the thread will basically exist forever. Now, if x no longer has a reference, okay? If there is no reference of x anywhere in a running thread, then garbage collection will remove it. Okay? So this will wait forever as long as some running thread still has a reference to x. If all the references to x are in blocked threads, then the garbage collector will remove it. Okay? So garbage collection also works for threads. Huh? Question?
Quelle est la méthode utilisée pour le wait?
Oui?
Un busy wait ou bien
c'est pas un busy wait.
C'est avec des signaux notifiés?
Oui, c'est avec des signaux. So it's not a busy wait. So this thing, what it will do is, it will attach a suspension to the variable. So the way this is implemented is that the variable knows what are the threads that are waiting on it. Okay? So the variable x here will have a suspension attached to it that will basically reference this thread. So that requires no execution time. So this is completely efficient. It's a kind of signal. Okay? So then when I need x, when I do x plus 10, this will do basically the plus operation requires both of its arguments. So this will actually do a weight on x. It will weight, and the weight x is implemented, so if there's any suspension on x, it will actually unblock the weight needed and it will continue. Yeah?
Pour les fonctions, par exemple, lazy recursive, est-ce qu'il y a de l'overhead de faire spawn des threads de cette manière-là?
Ah, so if you have recursive functions, so this is a very simple, so in a very smart lazy language, like Haskell, all the lazy suspensions are reused and it's very efficient. Okay, in Oz, the laziness will, whenever you do a lazy suspension, it will create another thread. Okay, but threads are very cheap, is the idea. So that's not so expensive, actually. Okay, so in order for this weight needed to unblock, let me just unblock it first. If I do a browse x plus 0, so x plus 0 will just return x, but this addition operation needs x, okay? So there's actually a weight. The plus operation needs both of its arguments to be values, and this will cause the weight needed to unblock, okay? So if I execute this, then I can see the results coming, okay? Question?
Quand vous dites que le spawner des threads, c'est pas très coûteux
Oui.
pour le processeur, est-ce que c'est pas très coûteux par rapport à un autre langage ou c'est pas très coûteux en général de faire spawn des threads au principe?
Okay, so the threads are actually the cost of a thread is just the cost of saving the thread state. So there's basically a small set of registers and also a stack, so that you have to also keep the stack pointer. So the threads are extremely lightweight, so you can actually say they're only a little bit more expensive than a procedure call, for example. Because compared to a procedure call, they have to save a few registers on the heap, okay? And it depends on how much state the thread has, okay? So a thread that is doing very small amount of work, the state is very small. So basically it's just a little bit more expensive than a procedure call. But you should not worry about the cost, okay? Because a small cost of execution is compared to a much simpler program, okay? So premature optimization is very bad, okay? So there's a famous computer scientist, Donald Knuth, who says that premature optimization is the root of all evil, okay? And he knows what he's talking about. So you should not worry about the cost of the thread at all. So you should write a program which is very simple, and at the very end, when you're actually selling it or something, then you can profile and see where the time is going. But usually most of the time is going in a small part, and usually most of these things will be a small percentage of the time, okay? So you really should not worry about the time percentages here, okay? Okay, so let me now give you a more interesting example. Let me do an example where we see in recursive functions. Let me show you an example with an infinite list. So fun lazy, int n, we return n followed by int n plus 1. Okay, so this is a recursive function which never terminates. Okay, so if you don't make it lazy, you should not write it like this, okay, because it will be an infinite loop. But in lazy programming, you don't have to worry about termination. So this can make the programs much, much simpler, okay? So let me show how this works, this infinite list. So let me create an infinite list that starts with 1. Okay. Browse L. So you can imagine what this is going to display, okay? When I run this function, it's not going to make an infinite loop. So the nice thing about lazy functions is you don't have to worry about infinite loops, okay? So this recursive function is an infinite loop, but we're only going to execute small pieces of it. So when I run this, this will basically do nothing. Well, it creates a lazy suspension. Does nothing. So how can we force this function to calculate? Well, the only way to make it do something is if we actually need the result, okay? So for example, if I want the first result of the list, L.1, if I want L.1, the dot operation will do a wait, and this will cause the body of the ints to be executed. But it will only do one step, okay? Basically, the recursive call will create another lazy suspension and it will wait again. You see, so it will only give you the first element, but then the rest will wait again, okay? So let me translate this into kernel language. So this will be a procedure. I'm not going to actually compile it, but one could. So ints n r is the result. I have a thread, and okay, inside this thread, I'm doing wait needed on r on the result, and then I do the recursive call, n followed by ints n plus 1. Okay, so this is not a complete translation into kernel language, because this part I'm leaving it the way it is here. So this is the body of the function. So I create a thread, I do wait needed on the result, and then I do a recursive call. That means if I need R, then this will unblock, and then I will execute this. So if I do L.1, this dot operation will do a wait on L, which causes the wait needed to unblock and execute this. So R will be bound to 1, followed by this. So this int's recursive call, because int is a lazy function, will create another lazy suspension. Okay? So the ints, when you activate it, it will only do a small piece of the computation, and then it will go back to be lazy, to sleep again, in a sense. It goes back to sleep, okay? And it waits for another needed. So that means each time you need a little bit more of the list, then you will activate a little bit more. And then, but the recursive call will immediately create another lazy suspension, okay? So if I want to see the second element, so L.2.1 is the second element of the list. So this will display, so this one will cause this one to wake up, because L.2 here, L.2 will be the variable that's bound to this, okay? You have to, if you want to really see the variables, you have to translate it to kernel language, okay? So if I do L.2.1, you see now I should display 2, and now the L, which is here, is 1, 2, underscore. So this final underscore is another lazy suspension. So you see, it only does little pieces each time, okay? So what if I need more elements? Let me show you an interesting function. Let me define a procedure that takes a list that's lazily generated and forces n elements to appear. Okay, I'll call this one touch, because it's like you're touching the elements. Okay? So if n is equal to 0, then it does nothing. Else, I do touch L dot 2 n minus 1. So this is a very simple function. Okay? If n is equal to 1, then I will do touch of L dot 2 with 0, which forces an element, because the dot operation will need L. Okay? So you see, this function really, this procedure really doesn't do anything, okay? But it forces the n elements of the list to be evaluated. Okay? Oh, I have to do a declare, sorry. Declare. I should use a mouse. Okay, and now I can do touch L. So L is the one we saw before, right? Is this thing. Let's say I want 10 elements. Okay, if I do touch L of 10, I force 10 elements to be computed. Okay? If I do touch L of 5, this will actually not do anything because these 5 elements already exist. Okay? So if I touch L 5, it doesn't do anything. But if I do touch L 20, then the first 10 elements already exist. Okay? But once it gets to the 11th element, it will force the lazy suspension to wake up again. Okay? And then you get here the 20 elements of the list. Okay? So this is an example of forcing the evaluation. So I have this infinite list here, which is going on forever, but it's not an infinite loop. Yeah? So everything is very well controlled here. Okay? Let me give you now another example. Do a lazy producer-consumer. Remember I showed you in the beginning of the course this producer-consumer. Well, let's make it lazy now. Let's make the lazy producer-consumer. Yeah? Question?
Je me demandais si les instructions qui étaient après le wait needed, quand on traduit en kernel, quand l'interpréteur traduit en kernel language, je me demandais si les instructions étaient toujours en dessous du wait needed, parce que si on a par exemple une fonction de complexité supérieure au temps constant, bah, ça pourrait être une optimisation de faire cette fonction avant le wait needed.
Oui, en fait tu veux toujours faire des optimisations, tu veux que tout se passe dans le même thread, c'est ça? Oui, on peut faire toutes ces optimisations. So you can do a lot of optimization here. Okay, this is only the semantics. Okay, now the Mozart system is actually executing it like this, but you can actually reuse the thread and have the same thread. Here the thread terminates, okay? But you can actually reuse this thread inside here with the source transformation. So I'm not going to talk about these optimizations, okay? But you can do it if you want.
C'est pas seulement ça. Par exemple, s'il y avait des instructions qui étaient juste au-dessus du wait needed, ben elles seraient exécutées avant qu'il y ait un wait, au lieu de l'exécuter.
Ah, tu veux dire la n plus 1?
Oui.
Tu veux l'exécuter avant?
Oui.
Pourquoi?
Parce que sinon, ça va attendre que le résultat...
Oui, mais ça peut être un très beau calcul. Et ça peut avoir une boucle infinie aussi.
Oui.
Donc, so the idea is you can take this n plus 1 and some of the computation here and do it before.
Yes.
Okay, but that's not that will not really improve the performance, huh? Because you have to do it anyway, before or after. Huh?
Mais si c'est en parallèle?
If it's in parallel, yes. So okay, so you can do that. That's optimization. If you have a multi-core system, you can do some of these on different cores. Okay, but you have to be very careful because the whole point of lazy computation is that you don't have to worry about infinite loops. So when you do an optimization, like moving this n plus 1 somewhere, you have to be very careful that you're not creating an infinite loop, okay? In this case, it's easy, it's n plus 1. But this might be big computation. I might be calling many functions here. Some of these might also be lazy. So if you do them early, maybe you're creating an infinite loop. So the whole point of lazy is that you do the minimum computation, okay? So let me now do a lazy producer-consumer. Okay. Remember, I did producer from L to H here. That means there was a maximum. Well, now I'm going to do producer with no maximum. So this function is actually the same as the ints function. Huh? L followed by prod L plus 1. Okay. And then there's a consumer. Let me make it also lazy with an accumulator. This will take, my keyboard is doing weird things, but it's okay. So here I will do app plus H followed by consumer T of app plus H. So this is calculating the accumulating sum. Notice I do not wait for the nil here, okay? I don't worry about the end because I don't worry about termination. Here I'm creating an infinite producer, infinite stream, and here I'm taking an infinite stream as input and making another infinite stream as output. But because the functions are lazy, there's no problem with that, okay? So I compile them. Let me now show you how this works. So let's browse S1 and S2. Let me put a delay in here so that you can actually see the lazy computation. Otherwise it goes too fast. I want you to see how it's working. Okay, S1 is equal to producer starting with 1. And S2 takes the consumer of S1, starts with 0, and does like this. Okay? So this is very similar code to the code before. Huh? If you look at the code before, let me go back up. So remember, this is the code we did when the functions are not lazy. Notice that we have this upper value, upper limit here. And notice that we have this nil case because the consumer has to stop. Okay? We have an upper limit. So the producer has a limit. Okay? That's the eager case. So in the case where it's not lazy, we call it eager. And the producer has to stop. Otherwise it's an infinite loop. Okay? But if we look at the lazy case, here, the producer does not have an upper limit here. The producer can go on forever, but it's not a problem because the producer is lazy, okay? The consumer also does not have an upper limit, okay? So the 0 is the accumulator, right? There's no upper limit. So this program can go on forever. So let me run this. So this does nothing, okay? Both of these functions are lazy, and I don't need anything yet. So how can I force it? Well, I can use the function touch to force this to make an output. Okay? So if I now do touch S2, and I say I need 10 elements. Okay, now look at what's happening on the right. Oh, what's going on now? yeah. I don't know why I turned it off. So there, yeah, well, let me do again. Let me now do, let me run it again so you can see it. Okay, I do touch. So every second, the producer and the consumer will make another element. So this is a lazy computation. So there's two streams. Okay. So if I make a picture of it, I have the producer, I have the consumer. This is S1. There's S2 here. And here I have touch. The touch is what needs the S2. So the touch will force the evaluation. So the touch will say, I need S2. It will do S2.2. This will cause the consumer to evaluate. And the consumer will do L of H bar T, which is S1. So the consumer will say, I need S1, and it will go back to the producer. So you see it goes step by step back from the output back to the input. So you have to understand how this thing is working. So there's no magic here. You are basically going from the output, and the control is going from output to input. Okay? So in a normal execution, the control goes from input to output. The producer is producing it, all the data goes through. In lazy, it's exactly the opposite. Okay? Everybody is waiting for the output. The output needs something. It asks for something from the consumer, and then the consumer needs its own input, so it asks the producer. So the control is going exactly back from output to input. And this is working through the wait needed operation. The wait needed is making the control go back from the output back to the input. But you see the program is very simple. So you understand how it works internally with wait needed. I showed it to you. But I know from experience that it's actually hard to understand this in real, how this is really working when I have a chain of things. Okay? It looks very simple. I have a producer with an infinite list, a consumer, which is an infinite loop here. There's no termination here. And then I just call both of them. So simple. So the code is very simple. So the programmer has a very simple view of things, but internally it's actually complicated. Okay? So let me explain that to you in a more detailed way. So the way I'm going to do that is I'm going to write on the board here. So let me, I want to write this on the board. I want to show you really how this thing is working. Okay? So let me see if I can make it like this. So I keep the code here. So you can see the code, and I will write here, and hopefully things will go well, okay? So I have a producer and a consumer. So let me translate them into kernel language. So the producer looks like this. Actually, this is probably not going to work so well. Let me, yeah, that's better. So the producer, okay? The producer is going to look like this. So NR, thread, wait needed, R, and then R is equal to N followed by producer N plus 1. Okay? And the consumer looks like this. And then finally I'll show you the touch. Okay? And then we'll show you, it's important, I will go through all the details so you can see really how it's computing, okay? Consumer, so let me see that I get the arguments right here. So there's an L, an accumulator, and a result. A thread end, a weight needed. Okay, weight needed of R. And now, the interesting thing about the consumer is it has a case statement. Case L of H bar T, then, let me make this a little bit bigger. So this will give you accumulator plus H, consumer, T, accumulator plus H, R. I know, the R is not needed, it's a function. Like that. Okay? So you see, this part, which I will make an orange rectangle around, this is actually the body of the original function. Huh? And here also it's the body of the function. So it goes after the weight needed. Huh? Okay, this is actually R. Is equal to this. Huh? And then we have touch. Okay, so the touch is a procedure. Touch L N. So here I'm just going to do the touch the way it is normally. If N is equal to 0, then nothing, I'm done. I don't need anything. Else, I do touch L dot 2 N minus 1 N. Okay? Okay, so now I'm going to execute this. Let me show you the body now. Where is the eraser? Here. So you can see how this flows from the back to the front. Okay, I have a thread. I have S1 is producer 1. I have a thread. S2 is equal to consumer S1 0. And I have touch. Okay, S2 maybe 10 or something. Okay, so this is my program. So when this first executes, S1 here is R. Huh? Is this R here? So it will do this suspension. Okay, so I'm going to write it like this. S1 is actually waiting in this weight needed. Okay, so I'm going to write it like this. Okay, S1 is a lazy suspension waiting for this. And here, S2 is this R, and it's waiting here with another weight needed. So S2 is going to be waiting, and here I have a bigger piece of code, the case statements. Okay, L here is S1. Okay, and now I do touch of S2 10. Okay, I'm doing the touch. So what happens? So when I do the touch here, it does S2.2, it causes this weight needed to wake up, this to execute. Okay? And this L is actually S1. Huh? So let me say this is actually S2, and this is S1. Huh? So you see, when I do the touch, it causes the consumer weight needed to wake up, because this R is actually S2. Huh? and then it executes the body of the consumer, this. Now, when you see, when it executes the body of the consumer, it's executing case S1 of h bar t. Case S1 of h bar t. This needs S1. So now we make one more step here. This case is now going to wake up this one. Okay? So this R is S1, huh? So when I do this case, it will wake up this weight needed, and then it will execute n bar prod n minus plus 1. So the S1 will be actually bound to 1 bar this. So you see how it goes backwards, huh? From touch, so that this is actually S2. The touch S2 causes this to wake up. Then I execute this body. Executing this body, this case, causes this one to wake up. Okay? Then I execute this. And now things are going forward again. Now I bind S1 to this. Okay? I bind S1, which allows this S1 to execute. S1 is now bound to 1 bar something, 1 bar something, and now I can execute this. And now in this recursive call, I'm going to do another weight needed, and this one also, and it blocks again. So you see, I make one step forward. So S2 here is bound to 0 plus 1, so 1 bar this. So the S2.2 is actually going to be this. So I actually have created a piece of the list, okay? So this is actually S2.1. If I display S2.1, it will now display 1, okay? So you can see how the control goes backwards through the weight needed, from touch to consumer, and from consumer to producer. And then I bind something here, and this allows this thing to go a little bit forward, and it allows this thing to go a little bit forward. So it goes back, and then I bind things, and I can go a little bit forward. And then I have my recursive call to touch, and if the n is 10, then I have touch L.2, 9, and then I will do all that again. So it's like waves going back and forth. I go back, touch, consumer, producer, and then I bind one element, and if the touch is not happy, if it continues, it happens again, until the touch ends, n equals 0. Okay? So that's how it actually executes. Now, when you write programs with this, usually you don't think of the execution, okay? But since in this course, I want you to understand the things, I want you to understand how it executes also. Not just how to write lazy programs, but also how to execute them. How they execute them. Okay, so now I will make this one go down again. So this can actually be pretty complicated execution, and we'll see more complicated examples later on in the course. But the code that you write is very simple, You see here, It's super simple, And it's very intuitive, okay? Okay, so let's make a small break now, and after the break I'll show you even more sophisticated things, lazy programs, okay? Let me now continue with the lazy execution. Let me now show you some more sophisticated programs using laziness. So the first problem I want to show you is called the Hamming problem. This one I will first do it on the board, and then I will show you how it executes, okay? Because it requires some explanation. It's a very interesting problem, and the solution using laziness is extremely simple. And if you want to do a solution using another approach, it will be much more complicated. Okay? So let me show you that problem and how we solve it using laziness. So first I'm going to explain it on the board, and then I will show you the code. So this is actually a famous problem made by a guy named Richard Hamming. So here's the problem. I have numbers of the form 2 to the A, 3 to the B, 5 to the C, where A, B, and C are integers greater than or equal to 0. So I want to make a sequence of these numbers in increasing order. So I want to generate the sequence of all numbers of this form. So 2, 3, and 5 are prime numbers. 2 to the A times 3 to the B times 5 to the C, but in increasing order. You see, it's not that simple, because when you increase these numbers, they get all mixed up, but you want them in increasing order. Okay? So this sequence will start with 1, of course. Let me call the sequence H. So it starts with 1. This is when A, B, and C are 0. And the next number is 2, okay? This is 2 times, and then these two are both 0. Then it will be 3. And now it's not 5, but we have 4. We have 2 squared, so we have 4. 5, okay? Now we have 6, 2 times 3. Okay? We do not have 7, but we have 8. Okay, so the 7 is skipped. This is 2 to the third, And then we have 9, which is 3 squared. And then we have 10, which is 2 times 5. The 11 is skipped. We have 12, which is 2 squared times 3, and so on. So you see, these numbers are actually generated from this formula, but we have to make them in increasing order without skipping any. So we have to generate them in increasing order. So that's the problem. We want to write a program, also an efficient program, that generates them in increasing order. And using laziness probably gives you the simplest possible solution to this problem. Okay? So the idea is the following. I start with H, which starts with 1. So I know it has to start with 1. Okay? Now I make 3 sequences. 2H, 3H, and 5H. So when H starts with 1, 2H will start with 2. Okay? 3H will start with 3, and 5H will start with 5. And now we can actually find the next element. Okay? The next element will be the smallest number from these 3 sequences. So 2, 3, 5. So the next element will be 2 from here. But since H now becomes 2, 2H will be 2, 4. 3H will be 3, 6. And 5H will be 5, 10. Okay? So now I have used up the 2. Okay? And now we continue. We look at the beginning elements that we have not used yet. 4, 3, and 5. And we pick the smallest one, which is 3. Okay? This is the next element of the sequence. Okay? So it's used up. And since now H has a 3, we can say 2H is 2, 4, 6, 3H is 3, 6, 9, and 5H is 5, 10, 15. So now we have 4, 6, 5, and we pick the smallest one. In this case, it will be 4. Okay, and we go on like this. You see how it works, huh? So we are generating in a kind of recursive way, huh? We start from the beginning of H. We find these three sequences, which are all the possible next elements. All the possible next elements will be either 2 times the previous element, or it'll be 3 times or 5 times the previous element. Okay? So the smallest of these three will be the next element, because it has to be one of these. Okay? The next element that's not written yet is always going to be either 2 times the previous element, or 3 or 5 times the previous element. So this is actually a proof that this is actually a correct algorithm. So we have this recursive approach. So how do we do this? We can actually program this using lazy streams. So lazy streams, we have a function. We can call a function, let me call it times, which takes a stream and multiplies this. So for example, times 2 will make it all the elements multiplied by 2. Okay? And then we have a function called merge, which takes 3 streams, S1, S2, S3, and creates another stream, which is always the smallest elements. It merging these the way I merged these. Okay? So with this, I can actually implement the Hamming problem. So I start with H, okay? So H is equal to 1, followed by, and here I will now merge of times 2H times 3H and times 5H. So basically this is the solution. So you can write it like this. So H goes to the times 2, times 3, and times 5. These are merged together. And this gives me H. Okay? So it's actually a recursive program using lazy streams. So if I use regular streams, non-lazy, then it's a problem, because I have to tell you the limit. Okay? So if I use non-lazy streams, I need the limits, the end. I need to know the limits. So if I do non-lazy streams in times 2H, I need to tell how many elements I need to do there. But that's not so easy to find, okay? Because 2H, I need maybe less elements in 5 than in 2. And as the H is growing, then maybe I need to change the limits. So this is actually very hard to program, the limits, okay? So this is actually very hard to program using non-lazy streams, because each of these functions needs to have a limit. And what happens if I need more? Well, I have to call it again with a higher number. So it's very hacky, okay? But with lazy streams, I don't need to do this at all. This is completely unnecessary. Okay? So let me show you how it works. So that's enough. Now I can show you the code. It's enough theory for this problem. So I have the times function and the merge function. Actually, let me do, to make it a little bit simpler, let me do a 2-argument merge instead of 3. But that's not changing very much. I just have to call it twice. Okay, so this makes it a little bit simpler. So let me show you the times now. times h by times n. So this is a lazy function. It takes a stream, h, and returns a stream where all the elements are multiplied by n. Okay? Case h of, let me call this one s. S of h bar t, then n times h followed by times tn. Okay? So that's very simple, huh? It's an infinite loop. It takes the stream s, it takes the first element, multiplies by n, and goes on. So remember that this is actually a tail recursive function. So this, but here in the lazy function, you can see that if I call it with s, and I need s, then I will do this. But the case s, when I need this, when I actually need the result of times Sn, it will run case of h bar t, and it will also need s. So the need will propagate backwards, from the result to the argument. Okay? Let me now define merge, also lazy function. S1, S2. Okay? Here I'm going to do, first let me take one element of both. So let me do it like this. H bar, T bar. So first I need one element of each. Okay? So basically I'm taking these two streams and I will output whichever of these two values is less. Okay, the smallest one. So if H1 is less than H2, then I will output H1 and I will follow it by the recursive call to merge again. Here I put T1, S2. Okay? So you see what I'm doing here. If H1 is less than H2, then the output will be H1. So I'm always taking the least. And then, when I do the recursive call, the argument is T1, since I've already used up the H. But it's S2, because I have not yet used H2. Okay? So if H1 is greater than H2, then it's H2, which goes to the output. And here it's going to be S1, T2. Okay? And here, in the final case, I have H1 is equal to H2. Let me make a comment. So you see how I'm doing it, huh? So here it's H2. If H1 is equal to H2, that's very interesting, because it's possible, huh? This is possible. Here, for example, I have 6 and 6. If it's equal, I have to eat both of them, huh? Because the 6 only appears once on the output, huh? So I actually have to, I can take H1 since they're equal, it doesn't matter. But when I call the merge, I have to eat both of them, huh? T1, T2. You see that? Here I have to eat the H in both streams. That's important, huh? So this is not the same merge as a sorting algorithm, huh? If you do like a merge sort algorithm, okay, then all the elements on the input, if there's 2 6s in the input, there have to be 2 6s on the output, because you cannot eat up the elements when you sort a list. Huh? So this is not the right merge for a merge sort, but in the Hamming problem, the elements only appear once on the output. So if I have 2 6s, I have to make sure that only 1 6 appears on the output. So I have to go farther in both of them. Huh? You see that, huh? So it's important to be very precise, huh? So this is almost the whole program now. So now I can actually do the create H. H is equal to 1 followed by merge. Okay, this is it, huh? So this is my program. I merge times h2 with times h3 and times h5. So I have two calls. So the reason why I do two argument merges to make this code a little bit simpler. Huh? You can do three-way merge too, but then you have to do all the different cases. Huh? And there's many cases, and sometimes the elements are going to be the same, sometimes they're not the same. So I don't want to do complicated. So the simplest is to do two argument merge. Huh? Notice there's no nil case here. Huh? Neither here. Huh? No nil. No termination. So all infinite lists. Huh? And so this recursive thing, where the h is both on the left and the right side, this will actually compute the value, the result. You see how short it is, huh? This program, huh? So I can browse h to see the result. So if you want to program this in another language, you can program this in Java or whatever. The code is much more complicated, okay? It's maybe a good exercise to try, but you'll see it's a lot more complicated. The laziness here is completely automatic, okay? But it's no magic. In fact, it's doing all the needed stuff that we explained. So this is actually working exactly the way I explained before the break. Yeah? So you can see here, it's showing 1. So far it's not doing anything. So if I want values, I have to ask for them. So I have my nice little function procedure, touch, that I can use. Huh? So I can say, oops, I don't want to remove everything. I can say touch h5 if I want 5 values. Well, I get 1, 2, 3, 4, 5. Okay. Let's ask for a little bit more. Touch h10. Now I see a little bit more. 6, 8, 9, 10, 12. So I get values, and I can do as many as I want like this. Now the nice thing is that this program is incredibly efficient. Okay? Because it's only using as much memory as you need for this, and there will be 5 lazy suspensions, okay, at the ends of this streams, okay, and you will only create as much of the stream as you need, and no more. So if I want 100 or 1,000, I don't have to allocate any memory. I don't have to pre-allocate an array of 300 elements or whatever. No, it's automatic. The laziness will automatically make the lists just as long as they need, and no longer. Okay? So this is a nice example of how laziness can make problems very simple. And this is extremely efficient because it uses the minimum memory, minimum resources, and it only allocates the memory when you actually need it. Okay? So that's nice, right? Having problem? Okay, let me show you now another problem, which is called a bounded buffer. Okay, so for this one also I will explain some things. Okay, so I will go again explain them on the board first, and then I'll show you the code. So a bounded buffer is something that's everywhere. It's something that's used in a lot of software, and it's usually not so easy to implement it, but I will show you how to implement it. First I'll show you what it is, and then I'll show you how with laziness, in a few lines of code, we can implement a bounded buffer. Okay? If you want to write a bounded buffer in Java though, it will be more lines of code than I show you here. Okay? So bounded buffer. So what's the idea of a bounded buffer? So a bounded buffer is actually used everywhere. It's a very common component. It's used to smooth difference in speed between producer and consumer. I'll show you what I mean. Between producer and consumer. So let me show you a simple example. Here I have a producer, and here I have a consumer, okay? And there's a string here, S. And the producer is making elements, and the consumer is consuming them, okay? And this is like a pipeline. Oops. Yeah, this is like a pipeline, and the producer, maybe it's doing computation, whatever. These could be things like video frames or web pages or whatever. There's a stream or bytes going through Unix pipeline. Okay? Now, the consumer will ask for an element. Okay? And this will cause the producer to produce an element. And then if the consumer needs another element, it asks for an element. And the producer will produce another element, okay? So this is the usual lazy approach. But this actually is not so good. We can actually do better. Because this is actually taking time. So if you look at the time here, so here's time. Here's the producer, the consumer. So the consumer is here, it asks for an element. It sends a message to the producer produces the element here. Okay? It does a computation, produce element. The consumer does something with that element, and then it asks for another element. And the producer produces, and so on. So it's like back and forth, you see? So actually this is not so nice, and the reason is that while the consumer asks for an element and the producer is making the element, the consumer is waiting here. Okay? And then when the element is done, it goes back. And when it asks for another element, again, it has to wait until the producer makes the element. And also the producer will have time where it does nothing in these times. So the time is kind of wasted here. It's not so nice. So the bounded buffer solution, the idea is to let the producer go ahead of the consumer. Okay? So here we have wasted time. So the bounded buffer solution is let the producer get ahead. Let the producer make more elements than the consumer asks. That means, let's say the producer makes 3 more elements. Okay? That means while the consumer is doing something else, the producer is producing more elements. That means when the consumer asks, the element is already there. The element is already available immediately. So when the consumer asks for an element, it's already there. The producer actually has made several elements, and it's already, so the consumer does not have to wait. That's great. And the consumer asks again, very fast, and again it gets the element immediately. So the consumer can go much faster. And also the producer is using these wasted times to produce extra elements. So in fact, using the bounded buffer approach, the producer and consumer can go a lot faster. So buffers are used a lot in real systems because it smooths the difference. You see, instead of wasting the time, you let the producer get ahead. So it can use all the empty time to make extra elements, even when the consumer is not asking, and then when the consumer asks, it immediately gives you an element, okay? So how does this look in the system? So the bounded buffer is actually a component, okay? It's an extra component. Okay, let me make a picture like this. So this is with no bounded buffer. I have a producer and a consumer. And both of these are lazy, okay? With the stream. This is with no bounded buffer. So with the bounded buffer, it looks like this. I have a producer, consumer, just like before, but I add an extra component in the middle, which is the bounded buffer. And all of these two are lazy. And the bounded buffer is very interesting because it's a combination of lazy and eager. So we're going to show you how to do this. So the code for the producer is the same as before. Okay? The code is not changed. Same code. Here also, same code. Nothing changed. So the producer thinks that the bounded buffer is the consumer, right? There's a string, S1, S2. So from the producer point of view, this is the consumer. And from the consumer point of view, this is the producer. Okay? So how does this thing work? So assume the consumer is not asking. Say the consumer does not ask for any elements yet. Later, maybe, but not right away. The bounded buffer, when you start it up, it immediately asks for elements. It says, give me I need 3 elements to the producer, immediately, even though the consumer has not asked for anything yet. Okay? So the bounded buffer has a given size. Let's say the size is 3. That means it has space for 3 elements. It could be bigger, 10 or 100, 1,000. In real systems, the buffers can be very big. Let's say it's very simple, 3. That means when the system starts up, the bounded buffer asks for 3 elements from the producer, even though the consumer has not done anything yet. And eventually, the consumer will ask for an element, and it asks the bounded buffer, and the element is already there, so he gets it immediately. The consumer is very happy, okay? And the bounded buffer gives 1 element then to the consumer, but now he only has 2 elements inside. So he immediately asks another one from the producer, because he always wants to stay ahead of the consumer, okay? The bounded buffer always wants to have 3 more elements than the consumer. So each time the consumer asks, the bounded buffer will ask the producer for another one so that it can fill it up again. Okay? So it doesn't always help. Let's say the consumer needs 4 elements. So it asks the first 3, it gets them very fast. But the 4th one, the bounded buffer, it's only size 3. It doesn't have the 4th one. So then the consumer has to wait, as before. So when the buffer is actually emptied, then it's the same as the previous. Okay? But if the buffer is reasonably sized, like 3 or 10 or whatever, that's very rare operation. It depends on how the speed of the producer and the consumer are fluctuating. Okay? But on average, the bounded buffer will not be empty. Okay? And if the bounded buffer is not empty, the consumer will immediately get things. And the producer is always happy because it's producing more elements. So the producer point of view, it doesn't really see much difference. The producer is producing elements, and the consumer is getting them faster. Okay? So you see, a bounded buffer is a very useful component in a stream system. And it's used everywhere in computing systems. You can write it in Java, you can write it in Python, you can write it everywhere. But it's actually really interesting to see how it works when you use lazy evaluation. Because then you can really see how the bounded buffer is doing its job. Okay? So I'm going to show you how this bounded buffer, we're going to build it together. It's only a few lines of code, but it's using lazy in a very nice way. Okay. see that? You see the bounded buffer now? Now I'm going to write code, huh? You understand what it's doing, huh? No questions on this? You see it's very useful, huh? So this is actually a generally useful component, and whenever you build computer systems, you need buffers. So there's hundreds of buffers everywhere in all the operating systems everywhere, and this is the reason why you have them, huh? Okay? So bounded buffer is a really useful and ubiquitous component. And you see it's extremely modular, because the producer and the consumer, they don't even know it exists. The code is not even changed at all. So it's actually extremely nice. You can easy to maintain, and you can tune it. You can change the size here. And so there's a trade-off, huh? The bigger the size, this will take more memory, of course, huh? The higher the size, the bigger the memory. You can say, let's just make it really, really big. Well, you don't want memory overflow, okay? So usually it has some size. And so the amount of smoothing it does, the speed increase, there's usually like an optimal point. Because when you make the size too big, it uses too much memory, okay? So usually the size is not enough to make a big problem, but still. So if you use Unix pipes, for example, they are buffered automatically, yeah? If I have inner sockets or pipes between two Unix processes, there's buffering there, huh? Okay, automatically. The operating system is giving it to you. I don't know exactly how big it is, but it might be, I don't know, 10 kilobytes or something. Huh? There's some buffer there. So these buffers are everywhere. Huh? Okay? Okay, so you know this. Now we go to the writing of the code. Okay, everybody? I can go to the code now. Now we will build this using laziness. And you'll see, I'll do step by step to try to make it extremely intuitive, okay? Because it's a small program, but it's doing exactly the right thing, okay? So let's write now bounded buffer, okay? So first step, I just want to show you what the procedure looks like. It looks like this. There's a declare, but let me only put the declare in when it's completely done. There's an input stream, an output stream, and a size. Okay, so let me wait a minute until the screen is brighter. So let's just start by writing this component. So remember we did lazy producer consumer, huh? So this bounded buffer, you can stick it in the middle without changing the code of these two. These two are both lazy, okay? So producer and consumer will both be lazy, and the bounded buffer is in the middle. So the bounded buffer, this is how it looks. It's a procedure. It has an input stream, S1, an output stream, S2, and it has a size. So when I call this, this will create my buffer. Okay? Very good. Okay, let me now do a second step. I want to just pass elements from S1 to S2. Okay, so I keep the same as before. Okay, so this is the first step. This is a simple thing. Here I have a loop which reads a stream, S1, and it outputs the same stream. Okay, it's doing nothing, okay? And the bounded buffer is S2 equal loop of S1. So basically, this is a bounded buffer that's not really doing anything. S2 is just getting the same elements are being passed. This is very similar to functions we wrote before. Huh? Remember the sum and the times and so on. They take an input stream, so I'm reading it here, an output stream. Notice this is a lazy thing, okay? That changes everything, of course. That means there's a weight needed here, huh? And so when I need S2, I will activate this lazy suspension of the loop, and then inside the loop I will need S1. You see, when I run the loop, so this will activate the lazy suspension of the producer. So you see how it's going, huh? So this is the first thing. I pass elements from S1 to S2. Okay, but my real bounded buffer has to do more than that, huh? So this is fine, because that's what the bounded buffer does. Huh? It passes elements, the same elements on S2 as S1. That's fine. But the bounded buffer does a little bit more. When it starts up, it immediately asks the producer for n elements. Okay? So basically, it lets the producer get ahead of the consumer. So when it starts up, this is fine. I can keep this. I can keep this. But it has to do a little bit more. It has to ask the producer for n more elements. N elements when it starts up immediately. Okay, so we'll add that. And then the next thing it has to do is whenever it passes an element onto S2, it has to ask for one more. Okay, it has to stay ahead. The producer has to stay ahead of the consumer. Okay? Okay, so let's do now the third step. So basically ask for n elements on startup. Okay, so when the thing starts up, it has to ask for n elements. So how do I do that? Well, I'm going to do something like touch, huh? But I'm going to use a list function. There's actually a list module. I'm going to do a little bit simple here. There's a list module in Mozart system with lots of list functions. Okay, so I'm going to use one of those to immediately, what does it mean to ask for elements? Well, it means I need the first n elements of S1. So I need n elements from S1. So if S1 is equal to A, B, C, D, E, etc., and assume that n is equal to 3, okay? But they're not computed yet. I need these 3. And then it continues. So I need these 3 elements. So there's actually a function called list drop. I'm going to use that just to be a little bit simpler. Takes a list and it removes the first elements. It's a function, so it returns some value. And here there's some value. So I'm going to do this. I take S1 and I'm going to remove, so list drop basically is like a touch a little bit, but it removes the first n elements from a list. And the result is this. But if S1 is a lazy list, this is going to cause the list S1 to be needed, of course. Okay? So this asks for n elements. Okay? Very good. Okay? So that's another thing. But we're not done yet. Okay? This is good. Okay? Asks for n elements immediately on startup. But we have to do a little bit more. Whenever the buffer passes H1 from input to output, it has to ask for another element. So it's not enough to ask for n at the startup. It has to keep asking during the execution. Okay, whenever the consumer takes an element, it has to ask for one more because it always has to stay ahead. So in fact, we need to do that inside the loop. Whenever we pass an element to the consumer, we have to ask for another element. Okay? Okay, very good. Okay, we're almost done now, actually. This is the fourth step. Fourth step. So ask for an element whenever a consumer asks. Okay. So this actually has to be done in the loop. Okay. Make sure I'm doing it completely right. It's here. So we need to this end is actually n elements ahead of S1. The end thing here, n is actually here. S1 is A, B, C, but n is actually here. It's n elements ahead. But if I give one element to the consumer, then I have to move end farther down. Okay, the end has to stay ahead of what I give, huh? So basically, I'm going to put end as an argument inside of the loop. Okay. Unfortunately, probably I will have to put this on another line, like this, because it's otherwise going to be too long. So I do like this, but not completely like this. So the loop is actually going to take end as an argument. But we need to ask for one element. But how do you ask for an element? Okay? How do you ask for an element? Well, it's very simple. You do n.2. It goes to the next one. Like this. Maybe if I do like this, I can keep it on one line. I like when the programs are short. Okay? So now we're basically done. Okay? This thing starts up. It asks for n elements. And this loop, as soon as the consumer needs an element, it will activate this, and it will immediately give h1, and it will do a recursive call, and it will ask for one more element from the producer. Okay? Like this. So the asks are going back, like that, from consumer to producer. There's only one small problem here that we can fix with concurrency. So this is logic is completely fine. The only problem is that this list.drop call, it will only return when end actually gets the end values. But I don't want that. I want immediately to do this. This has to be done concurrently, actually. Yeah? So the final step is to put all these asks in their own thread, and then it's done. All asks in their own, because we don't want them to block the program. You see, we're actually combining lazy and concurrency. So how does it work? Well, it's very simple. This thing has to be in a thread. Okay? Otherwise it's going to block here until the producer actually gives you the n elements. So there's no advantage. But there's no way, the reason that we have to wait, this we can be waiting, can be done in another thread. There's no reason why this should keep us, so this will run by itself concurrently, and it will ask elements from the producer, and hopefully it gets ahead of the consumer, and this one, the loop will keep elements to the consumer, okay? So we're almost done now. If you're alert, you will notice there's one other small thing we need to do. Do you see what it is? It's almost the same as this. We need to do one more thread, actually. No? You don't see? So there's two places where we ask the producer. On the startup, we ask for n elements, and whenever the consumer gets an element, we have to ask the producer for another element. So we do n.2. But we don't want this either to block the execution. So you notice that it's an interesting combination of threads, and so let me make it now. Let me make a few extra lines, whatever. I don't like extra lines, but in this case it looks nice. So this has to be in its own thread too. Oops. And now it works, okay? Now, this is it. This is a complete running bounded buffer. It does everything perfectly. So it passes elements from producer to consumer. It asks for n elements in the beginning. That's how it should work, yeah? And whenever the consumer gets an element, it asks for another one from the producer. So the end is always staying ahead of S1. N is always n elements farther than S1. Or it tries to be, because it depends on the speed of the producer. It's always trying to be n elements ahead. Okay? Okay. So this is the most subtle program that I'm going to show you today on laziness. You see that introducing the lazy concept can let you do very interesting and smart programs. So if you want to write this in another language, it will take 3 or 4 times as many lines of code. Huh? And you will never be able to do it so short. But this is telling you exactly what the bounded buffer is doing. Okay? And maybe one final comment here. So I will show it, but maybe next week, because we're at the end now. So one final comment here. The bounded buffer is actually switching between eager and lazy. That means the bounded buffer asks for 3 elements, right? So the producer is pushing the 3, but once it has the 3, it stops asking. Okay? So then the producer stops. So while it's asking, the producer is actually eager, but when it stops, the producer is like lazy. So it's like switching between eager and lazy. That's another way to see it. Huh? When it fills up, it becomes purely lazy. But as long as it's not full, it's actually eager. The producer is running freely. Yeah? As long as the buffer is not full, this guy is running as fast as it can. Huh? So it's eager. Huh? But once the buffer is full, then it's only the laziness that drives it. Okay? On this side. But of course, for the consumer, it's better if the buffer is full. Huh? Then the consumer will immediately get, whenever it asks, it gets something right away. Okay? Okay, so let me stop here today. So this is a fairly subtle lazy program, huh? I think you agree with me, right? That it's not so simple, but it's worthwhile to really understand how it works. Because this will, if you understand really how this one works, then you really understand laziness. Huh? And you can use it in your programs. So this is a general technique, lazy. Huh? Sometimes it's called pull. There's push and pull. Huh? You can program it in any language. But usually it's more lines of code than here. Question?
Could you also put the code examples on Moodle?
Yes, I will take this file. I will add a few comments to make it nicer, and I put it on the Moodle. Huh? I will do that today. Okay? So this file will go on the Moodle. Okay. Very good. So that's all for today. Thank you.